A great pleasure to be back at Rutgers and DIMACS. Rutgers, my undergraduate institution. I had an undergraduate course with Fred Roberts, and there he still is. I was telling Dave, he still looks the same to me. Our difference in our age hasn't changed all these years. And so, yeah, I mean, so it's a real honor to be able to speak in this tribute session to David Johnson. Dave Johnson is a great friend, longtime colleague, and champion of algorithmic research. I mean, he had a particular love for the bin packing, but also a particular love and interest in the traveling salesman problem. In 2012, there's a movie that came out called Traveling Salesman, directed by Timothy Lansone, and won a number of important awards. It's centered around a very fast algorithm showing P is equal to NP and the societal implications of that, whether you should hold it to NSA or what. So good points and bad points of such a thing, not unlike the discussion currently going on about AI. So this is centered around the TSP and NP. And of course, if you're doing something with P is NP, you have to reference David. Let's see if the sound works. No sound. Oh.
Ridiculous. We're not even talking cutting-edge theory here. Gary Johnson, guys in the 70s, showed that fundamentally all these complex mathematical problems, knapsack, SAT, whatever, they're all the same problem.
Solve one, solve all.
That's what.
Exactly. Solve one, solve all. So I watched this movie again this past weekend, and I decided, well, I'll go and get my copy of the book from the guys from the 70s, and I pulled out this nicely used copy. And thought, well, there must be a nice quote about in the TSP. And I didn't have to look hard. On page 4, they introduced a problem. The first problem that they mentioned is the traveling salesman problem. I mean, David really had a love for the TSP. And also, as far as breadth of work, I think he's probably the greatest champion of the traveling salesman. So pretty much any aspect of the TSP he's worked on, including having a full course given at Columbia. This sort of abstract drawing of David is what Mihalis mentioned. He's a marathon runner. He's actually a fantastic runner. So when I lived in Madison, I would see him coming down the streets, and a person of his size being able to carry that speed was fantastic. This is a copy of Runner's World, the main runner's magazine journal in the US. This is David in front of the lead group of the Boston Marathon. One thing I did notice, though, this last night is that David's shoes is the same shoe that I had in 1975 when I entered Rutgers. That's the Onitsuka Tiger shoe. They were ubiquitous out there. And you can't get them now anymore, but a couple years ago they started making replicas. So I wore mine to show off and honor David. And they match well with Tammy's designed VRP socks. Yeah. So David's leadership was not only in the research community, he was also interested in outreach. In particular, he did a great job at trying to straighten out some of the wildly misleading claims that are made in the popular literature or in scientific literature about the traveling salesman problem. This is a letter correspondence that he wrote to Nature that was published after an article appeared, a survey article on sort of neural networks and sort of biological inspired methods, and trying to straighten out the claims that you really need to compare with existing technology. A similar article appeared in the newsletter appeared in New Scientist when there was ant colony optimization, which nothing against ant colony optimization, but it was greatly overstating its use in the TSP. And David set out to correct these. And I have to say, we, as a community, we really missed this person of such David's stature going out and trying to straighten these things out, because these occur over and over again in the traveling salesman. For example, in 2018, there was an article about quantum computing, and it's in the Washington Post, and it says that a 22-city problem take 1,000 years. Now, I don't remember what you had on that chart, but it was less than 1,000 years, I think, for 22 cities. Yeah, so well, I don't have David's stature or the great computing ability of John, but Dave Applegate and I had a fast implementation of the Bellman-Held-Karp algorithm, and it takes 0.005 seconds. If John tweaks it a little bit, probably 0.001 second, which anyway, it's a lot less than 1,000 years. So that was the best I could do, and I thought, oh, that was nice. There was so I'm not getting Elon Musk type of coverage on Twitter, but there was quite a number of retweets and comments, enough that the Washington Post contacted me about this, and eventually got in touch with the author. We had some interaction. Eventually, this appears on Scott Aronson's blog on quantum computing. I thought, all right, good. I did my bit, and not David Johnson's stature. But then I just spent a year in Germany, and Martin Grütschel, who's a German optimization, sent me this article to the Tagesspiegel that was 22 years on a laptop computer. They upgraded, now it's 22 years on a supercomputer. So I obviously is missing this David's ability to correct these things. But it was not only these trying to correct things, he's also played an important role in the positive, the better articles on the TSP. So this is one that Gina Collada wrote. Actually, John and I just had a discussion. There's small things that tried to correct and didn't correct. But overall, the picture she paints is pretty much correct, right? That getting exact solutions are difficult, but for many practical problems, we can get quickly solutions that are suitable. So this was a while ago, 1991. John and David had already been working on 100,000 point problems, enormous size, and getting quite good approximations. And so when you see this article that she has a good understanding of what the issues are, well, you look further. Well, the person she references is David Johnson. So David sat down and somehow was able to convey the real spirit of the TSP, which is difficult. If you spoke to reporters in newspapers, they just want to put some flashy little thing, misquoting you slightly to change the meaning. But somehow he got the message across. I also like this that John mentioned in his talk. This is where this quote appears about that Christoph Paperinitrio said TSP is not a problem, it's an addiction. Rereading that article, it's available online. This is actually nice, this archive that New York Times has. He had actually another statement saying at the time it seemed true, but now it seems a lot truer. And as he mentioned in his talk, 40 years later, I think even truer still. He's still working on the TSP. So I like this article, except for maybe the title, long baffling, slowly yields. I might have put very slowly yields. These are three of the main theoretical topics on the TSP. The first is the most basic question, right? How quickly can you solve an n-city TSP? Goes back to Carl Menger, the sort of Menger theorems. Menger. His father is a great economist, Carl Menger with a C. This is not him. This is the Menger's theorem. How fast can you solve n? He knew he could do n-city TSP. He knew he could do it with n factorial, n minus 1 factorial. In 1962, using dynamic programming, Richard Bellman and independently Richard Karp and Michael Held showed an n squared 2 to the n algorithm, much better than n factorial. And the algorithm is simple. I mean, I explain it in detail in just about 5 minutes, but in 30 seconds, you get the idea. 2 to the n, you're looking at every subset, but you look at a distinguished point in every subset. That's how you get the n 2 to the n. And you find the shortest path ending in that specific point. Using that, just with n comparisons, you can work your way up from the path of length 2, 3, 4, and go up all the way up. Get n squared 2 to the n algorithm. Only takes like about a page to describe in their papers. The remarkable thing, though, is there's no improvement. There's not epsilon improvement in all those years. So Gert Roniger had a nice survey on algorithms for NP-hard problems. And always he's challenging is to replace that 2 with 1.99 to the n. No progress on that. Special cases, yes, but in general, no progress. A second point, and this is one I'll talk about later because it was about the long interaction with David Johnson, is the BHH constant. So you have points in the unit square, random points. What's the length of the tour? It's going to be beta times square root of n. Again, I'll talk to it more. But this was proved in 1959, and only epsilon improvement all these years. Again, the combinatorics here is easy. The lower bound is just coming from, well, if a point has to be connected to two others, to get this lower bound, they're just connecting it to your nearest neighbor and your second nearest neighbor. That gives a lower bound. To get the upper bound, they split the region into strips, get the tour along, take the strips just in order, the points in order in each strip, and then connect them up. That gets the upper bound. Very simple. The probabilistic analysis is a little tricky, but the combinatorics is simple. There are only epsilon improvement, only recently. Approximation methods for symmetric TSP. This is Malice just mentioned, the Christophidis algorithm. It's also appeared in the Russian literature. 1.5, simple algorithm. Spanning tree, you get a matching to pair up the odd degree nodes and find a walk and shortcut it. So the whole thing only takes about 5 minutes. Only epsilon improvement, and this is very difficult, epsilon improvement, all these years. So I wouldn't say that it's back in 1992, it was slowly yielding, because it hasn't yielded much. Even on the computational side, this is a problem that David J. generated in the year 2000 for the TSP challenge. 100,000 points, well within the range of what we can attack with LP methods, except we can't find the optimal solution. That's 23 years. Hasn't been any progress. All right, getting a little bit closer. So we spent a lot of time with different groups of people. Our main colleagues are Dave Applegate, Bob Bixby, Masha Quatel, and had 2 students, Daniel Espinoza, Marcos Caculier. Kjeld Helsken is the great tour finder, and 2 researchers from Bonn, Stefan Hogarty and Stefan Schroeder. All together, with a lot of work, we have 4 zeros, 3-8 approximation. I have to say 4 zeros is nice, sort of a target, because the mixed integer programming code, Cplex, Gurobi, and others, that's when they stop and say they're optimal. By default, Cplex reports optimal, means it has 4 zeros. 4 zeros and 9, 4 zeros and 3. More recently, we showed that you could reduce the problem, starts as a complete graph. We're now down to a graph of degree less than 5. So it really is a graph problem at this point, but we haven't solved it. It's true over the last 4 years, this approximation we lowered by 50%. So you might say, that's great, are you going to finish? Well, don't forget Uncle Zeno, right? We can lower it by another 50%, and I'll talk again in 5 years, and it still won't be done. So, still baffling. Nonetheless, I don't like these articles in the like Washington Post saying 22 is impossible. Even more respected places. So the last session was devoted to the Amazon contest. The blog that they're announcing the Amazon contest, they had a statement, it's NP hard. So all but the simplest instances, it's computational intractable. Oh, I really don't like that. Right? I tried to spend most of the last 30 years trying to convince people that the opposite is true. Right? You have a particular instance of an NP-hard problem. You have the whole world of mathematics, computer science, optimization all at your back. Well, don't just give up. Go ahead and try to solve it. Right, this is a particular instance. All right, but all but the simplest ones. Well, in 2020, a Dutch firm sent us the biking distance between every historical site, every monument in the Netherlands. So some 57,000. So they computed 1.6 billion distances. This was a symmetric problem. In Holland, on the bike path, you can go either direction, which seems strange to me, because I was just in Amsterdam a couple weeks ago, and they look like they have 2 sides of the path. But they said every bike path can go in either direction. So it's a symmetric problem. Even a low-order polynomial algorithm is going to take a long time. This is doing 1 billion operations per second, which you really can't do with this type of large memory. Nonetheless, a few months later, we'd solved it. With Kjeld, Daniel, and Marcos. And it wasn't just luck. We solved similar sized problems with Google distances several years earlier. And by solve, it really means solve. Not just found a good solution. This solution is optimal to that number of meters. The distances were in meters. This is a cartoon appeared in a Dutch newspaper. There are a number of Dutch people here, but this is easy enough to read. This is the monument to the researchers who computed our bike route. And this wasn't any new wild technology. What we used to solve it goes back to Danzig, Folks, and Johnson, the first real computational paper on the TSP using linear programming. It's Bob and Danzig, so it's going to use linear programming. They solved the 49 city problem, and exactly, they knew it was optimal. They give a 1-page proof, you can't read it, but this is actually proof that tour is short as possible. Right? This is what the Washington Post is reporting that we can never do. Their method, well, rather than thinking about a tour, you think of it as a graph problem. So either yes or no, is this edge in a tour or not? So you have the 0, 1 vectors picking out the tour, picking out edges in a tour. Once you have that, it's not a great step to get a linear programming approach. Right? You just need linear inequalities that are satisfied by all those tour vectors. And optimize the TSP. Well, every tour is a tour vector, so it's in your solution set. So the optimal solution to your linear programming will give you a lower bound on TSP, which is, that's the hard part, right? To show that your tour is optimal, you have to prove there's no better one. Okay, yeah, but if you're really interested in practical computation, you look at that and say, I got to get an optimal solution to the LP? The LP solvers don't give optimal solutions, typically, right? They give you a solution that, for numerical reasons, it may not be really optimal, right? So how am I actually going to optimize the problem? Well, luckily, the beautiful thing about LP that we all know is you don't need to get an optimal solution to get a bound. All you need is a dual solution. Every solution to the dual problem bounds the primal problem. So I just need a feasible solution to the dual. But again, if you work in numeric analysis, how are you going to get a feasible solution to such a big system of equations, right? Well, for this particular type of LP, the variables are 0 and 1, so they're bound between 0 and 1. That gives you in a dual these two identity matrices. So you give me any dual solution, I can make it feasible. Hey, it changes the bound a little bit, but you can make it feasible. So you give me any dual solution, I can get a lower bound, valid lower bound for the TSP. That allows you to use the LP as a black box. You don't have to check that Cplex is correct, right? It just gives you something, and you turn it into a correct proof, right? It gives you something bad, you get a bad bound, but you're not going to get anything wrong, and that's what we use. David Johnson himself, hopefully the sound works well enough, you hear him commenting on the use of this linear programming methods for the TSP.
When 20 years ago, when I worked on the TSP assembly plan, invited to solve 1,000 cities, I couldn't believe it. That would ever happen. But using, take 5 instances of random points unit square, I ran a counterpart on these, on 10,000 different compound city instances. And the running time range from 773, like 8 hours to solve them all. This is a logarithmic thing. The running time is a logarithmic.
So he says he's generated 10,000 instances of taking 1,000 points in a unit square, and all of them are solved with TSP. This is the log. This is the plot of the runtimes. This is the log of the runtimes. And it's not just those 10,000. We actually, for the same reason that I'll describe in a minute, actually did 100 million instances altogether, running from n equals 10 up to 2,000 of two types. One are the ones that David talked about, random points in a unit square. The other are random points in a unit square where you identify the two edges. So it's like the torus, right? Wrapping it around. The reason for those goes back to this BHH constant that I mentioned earlier. That arose in one of the earliest mathematical paper on the TSPs by the statistician, Indian statistician Mahalanobis, who was a great person. He was interested in income inequality in India. And he proposed to help the jute farmers in Bengal, help them by getting an understanding of the quality of the soil. So he wanted to do a random sample of the farming regions in Bengal. To pose that to the government, he needed to give a cost estimate. The major cost was going to be moving people and equipment from place to place. So he needed to give an estimate on the expected cost of doing an endpoint tour in a unit square. And what he argues is that it's proportional to square root of n. If you read his paper, you realize he could have turned that into a proof, but probably figured the government officials don't need an actual mathematical proof, just gave them a small argument. So this was an expectation that BHH, which is Beerwood, Hoth, and Hammersley, they show it's actually more than an expectation. It grows almost surely to some given value, beta times the square root of n. So as n goes to infinity, with probability 1, the length of the optimal tour is going to be beta times the square root of n. Beta is a constant, like Planck's constant. Except for, unlike Planck's constant, we don't know what it is. In this paper, is what I mentioned, it had these sort of easy combinatorics, but hard, tricky probability to give this bound. So Gillian Beerwood, I was giving a lecture in Dublin at a big OR conference, And I was really intrigued because she wrote this one paper and then went off and had a career in a PhD and a career in economics and worked on traffic flow. So she is in England. Now it's popular in game theory. She wrote papers on showing that if you increase the width of a certain road, it was going to make the traffic worse. In practice, it made the traffic worse. Yeah, and so I spent a long night trying to find, because she's elderly, spent a long night trying to find her. And eventually I found a Jill Beerwood that was running a newsletter from some church group. And so I sent her an email, not expecting anything to happen. But the next day she writes back and saying, yes, I am the Jillian Beerwood. And she passed away a year later in 2020. And so this statement that she made is really poignant. She says, how far have you progressed the problem? Right. This is 1959. There had been essentially no progress. There ipsilon that happened, some of it a little bit later after she passed away. Yeah, so these problems are not, it's not slowly yielding. It's very slowly yielding. So this was our interest in these computations, to use computational tools to see whether we might give any hints about where this limit might be. So, to give you an idea of it, this is for n equals 50, these are the histogram, not like David Johnson had a histogram of the running times. This is a histogram of the tour lanes. You see they're sort of normally distributed. What I'll show is a GIF that I'll slowly increase n up to 2,000. And what you'll see is the mean will be moving this way, getting smaller, but the distribution tightening. The BHH theorem says if that continues, this is eventually going to spike around some particular value, which we don't know what it is. All right, but we have pretty good evidence that the trend is coming down. You see the scale here is up, going down 7.3. The ones on the torus, which asymptotically give you the same value, but they don't have this nastiness of having to worry about the border effects. So it's actually converging much faster. It looks like to us it's going down to this number, 71240 as the constant. And I was quite sad. I thought we were done, right? I'm just a person who grew up on farms of southern New Jersey, just an easygoing guy. And to me, actually, the biggest thing, I was most interested in, that 100 million, we didn't skip any instance. That was one stream of 100 million random instances. We solved every one. Again, these newspapers say that in all but the simplest instances, you can't solve it. To me, that was the most interesting thing. The second most was getting this, but my colleagues, the two Davids, David J. and David A., these are scholars. So I get this message from David Johnson thanking me for doing all this data, and we should get a paper, applicate Koch-Johnson. But we noticed that your numbers for 20 were a little bit higher than the number for 10, and that needed some explanation. So this is 2008. All right, they're scholars. I mean, I thought, wow, so it's bigger. All right, so jumping ahead to 2009, now they've recruited Neil Sloan to help them in their analysis. This is a talk David Johnson gave at the ISMP in Chicago, some 75 slides, including a detailed analysis of some, they're not really theorems, but they're heuristic arguments about explaining the tour length and trying to figure out why it had that certain shape. Very, very great. And I thought, that's great. But I get a note in September 30th, David says that he was ready to get the journal version ready by year end. But David A. says, oh, I think there's some more things we could look at here. Again, these are scholars. So we jump ahead to 2014. David gives two talks at Waterloo, Copenhagen. Now he's up to 104 slides. But I'll just show you the last one. Not done yet, right? Still some conclusions and open questions. More that we have to do. Sadly, David passed away before we finished this project, and David and I, just without his, David J's enthusiasm and energy, we haven't completed this paper. I still hope that's something we do. Actually, I was inspired by it that you finished yours in 2020, and you started in 2008. You notice we also started in 2008. So here in 2020, this is not that much longer, so we could still handle this. So this thing about being an addiction, clearly it is addictive. right? And I don't claim to be immune from that. In fact, just last month, we got some new results together with Dave that go back to earlier than 2008. So we had discussions with Kjeld Helsken and Andre Roa. Andre Roa is now the vice president for engineering of Meta. He had a similar position in Google. Trying to develop, like as John was saying, understanding of getting problems of postsynapse asymptotopia. So these are problems with over 100 million points to visit. When we're working with Andre, we had a big data set, but it's only a 2D, so it's just they knew where stars are, but didn't know how far they are. I mean, it's much more difficult to figure out how far they are. So our problem in those were just moving a telescope around to visit them all. Now, using some parallax information, astronomers can build these data sets where they're getting pretty good estimates about how far they are. So we get 3D Euclidean instances. These are two databases from the same group, giving two versions of it. And we have approximations that are 3 zeros. Now, my dream was always to get 4 zeros, so I don't consider this done yet, not ready for publication yet. We have to turn this 1 into a 0. I don't care much about this one so much because I figured if we can get that one, then while we goes more time, we could have gotten that one. But I really want to get that one. Yeah, so these thing about computational work from the TSP, you can always get bigger, right? There's always bigger problems. And if you want to go big, astronomy is a way to go. I mean, those guys have data sets. So these are all 3D examples where the distances are the 10th parsecs. So their distance rounded to the 10th parsec, which is wildly a lot of hubris there because they actually don't know to anywhere near that degree of accuracy. But that's our distance function. And we solved the example of that at 109,000 points. Actually, Bob Vanderbilt was the first one who pointed me to this HYG database. And I was quite surprised that we solved that because you remember I said that we haven't been able to solve this 100,000 point problem, yet we solved that optimally. And so this one on 2 million points, we have 5 zeros. I mean, that's wildly accurate, right? That's like going from here to California to San Francisco by only being a car length away from optimal. And it's wildly better than we have. In fact, I already knew this from some small examples that for our LP methods, 3D examples seem to be easier than 2D. So we're getting, it's surprising to me to that. But again, I knew that, and I thought, all right, so that's that. David Johnson's a scholar. So as part of this course, they actually had a student, and they worked out how to do 7D. It's a little bit hard to get the Concord code to work correctly with that. And it shows that these are running times. The running times are getting dramatically smaller if you go out to 7D, which makes me think that if we lived in a world like with a string theory, say 11 dimensions, yeah, probably the TSP wouldn't be this poster child of NP hardness, right? It would be would be easy, the problem. But we don't. What's that? Time could be a dimension. I don't know. I mean, it just seems like well, I don't know. Actually, if we ever do star travel, maybe it's going to be something different, right? Yeah. Yeah. But I want to say, even though they seem to be easier, notice that these approximations are getting worse. 5 zeros approximation. Then we go up to 10 million points, we have 4 zeros. The 100 million, we have 3 zeros, the one I want to turn to 4. Once we get out to 1.3 billion, we have 2 zeros approximation. And there are some reasons for that. I mean, one is we're relying on tours, right? We get a tour and a bound. We have no experience on tours of the size. We don't know if we're actually close to optimal. But I think more important is the LP technology that we're using. It's changing as the problems are getting bigger. So the cutting plane method for the TSP, you get the relaxation, solve it. If it's not a tour, you find some more inequalities to add and resolve it. So it's a sequential process. Each time you're solving, because you're doing a sequence of LPs, you're using the simplex algorithm. At the moment, there's no effective parallelization of the simplex algorithm. So you're running a sequential process where each major step is sequential. And for this 2 million point problem, the LP solves are taking 99.99% of the time. So it's not leaving much room there for combinatorial improvements, right? So you can't rely on just doing the simplex method. So this is the larger examples, the 2 million, 110 million, 1.3 million, 136 million and 265 million. These are the size of the LPs. Now, the 2 million one, we really are using cutting plane method, as you expect. Except for one difference. How did I get around this 9.99? Didn't know how to get around it. So I just started using randomization. So I had 32 cores running the cutting plane method. After every couple of days, I'd shut down 28 of them and repopulate those ones with the best of the remaining 4. And save all the inequalities they added to reuse. So it was just doing something stupid, but keep it going. I have said a lot of computer scientists here. The best gift computer science could give to operations research would be a faster simplex algorithm. This is the workhorse of operations research, and yet it's hitting its limits as problem sizes are increasing. All right, but one nice thing about the cutting plane method is we're really in Concord really careful about discarding inequalities and finding. So you not only have to have inequalities, you can't use the complete graph. So you're having a subset of edges, and we're really careful about throwing things in and out. So we actually, for this 2 million node problem, we only have 4 million variables, only twice the number of n, which is twice 2n. Once we get up to 10 million, we can't use the simplex method anymore. It takes too long. So what we did there is to use the barrier algorithm. So what we do is work hard to accumulate as many inequalities as we think we need, right? And filtering them out, using little linear programming problems to filter them out, get one big LP, one set of edges, solve it with the barrier algorithm. Barrier is the interior point algorithm. Gives us a primal dual solution, and then we iterated that process 7 times. That got us down to this 4-0 approximation. Barriers, all right, it's not bad. Solving those big LPs are still taking only 172 hours. The problem is they take a lot of memory. Bob says it's no problem solving them, but the Cholesky factorization just takes a lot of memory. So I wrote to Ed Rothberg, who John mentioned. He's now the one of the leaders at Gurobi, earlier at CPLEX. Said, is there some way I can trade off in your code running time for memory? I'm willing to spend more time, but less memory. But I said, no, the Cholesky factorization is going to take that memory. So once we get up to this, so the size here, this is 462 million non-zeros. Once we get up to this one, it's 50 billion. So I mean, it's a factor 100 larger. We have no chance of doing that with the barrier algorithm. All right, so luckily, Dave's involved in leading the group at Google, making a first order method solver. So they like to call it matrix free. Is that your term, matrix free, or everyone uses that term, matrix free? That's what Miles uses.
Matrix free,
Yeah.
it means matrix factorization.
Yeah, so no factorization. So all they're doing is their steps of their algorithm, it's a first order method, are doing matrix vector multiplies. So you can parallelize that in a great way. They're doing primal and dual steps so they get bounds. And amazing to me, somehow it took a long time. I mean, Dave and I have been discussing this, and he every 6 months or so sends some update. Well, this past April, he sent me dual solutions for these 2 problems. And that's not the end of the story. He's sending, so I'm only giving him a certain number of variables. You need a bound for everything, so I have to compute the reduced cost. So I have to price out the rest of it. And so it still takes some work. But as of April, we have now those bounds. And these are with a single LP on these 2. I just find it amazing that they can give accurate solutions to LPs with 50 billion. Of course, there's always a bigger problem, right? So this 1.3 billion is every star for 3D that they have enough information from the Gaia mission, data release 2. That one we're not able to, at the moment, not able to solve a single LP. This weak approximation just goes back to what we started with Andre Roa in 1995, that we just do a subdivision of the problem, find cutting planes, inequalities for each region, make sure that your weights are such that the dual solution is valid, and we can get a 2-0 approximation. Google's very interested in solving bigger. They don't really care about visiting. I don't think Google really wants to visit 1.3 billion stars.
I'm not allowed to comment.
I know you always end it. Your non-disclosure agreement comes up a lot in our conversations these days. But they're for some reason interested in big LPs. And this is just an example of a big LP. So that's what I believe the Google group is interested in. As I said, I'm more interested in finishing this work and getting this one down to another 0. So 4-0 approximation. So it has this gap, right? The gap is the Tor length, our Tor length that Keld has computed with LKH, specialized version of his LKH code, and our price LP bound. Now, the gap comes from different reasons. One is, well, maybe Keld doesn't have the optimal solution. There's some going to optimal solution. Well, maybe I don't have the right cutting planes. So difference between the LP and the optimal length. Maybe Dave has computed the wrong LP value. Maybe I didn't give Dave the right edges. So I have to price the range. So of those are hard to estimate, any of those, except for that last one, because he gives me the dual solution. I can compute what the LP value is, and I know our price value. So actually 3% in the gap was that's actually we had neighboring office, and anytime something go wrong, Bixby, Dave and I had neighboring office at Rice. Anything somebody would say, no, I'd yell out, not my fault. Well, this one is my fault. That 3% I just gave Dave the wrong edges. The remainder, we don't really know where it is. What I suspect is there actually is not much room here, just based on the solution they gave for 10 million. And they have this primal dual. I mean, how confident are you that we're within 10 to the minus 4?
Well, in terms of how 10 to the minus 4 is defined, sure.
I think we all have a definition of 10 to the minus 4 in our heads. I mean, anyway, they have a primal dual solution. I don't suspect that there's much room to grow there, to prove there. Not in terms of this big percentages. The big things are Keld's Tor and my cutting planes. I would guess that just because Keld is smarter than I am, I guess the main trouble is there. And now, it seems like, and this is true, this all works nicely independently. So Keld's finding the Tors, I'm getting the cutting planes and edges, Dave gives me the dual solution, and I compute the bound. So nicely separated. But the parts do interact. So Dave sent me the thing. The first thing I did was compute the values, then computed the graph. So each node, each point we want to represent, I computed the 10 shortest edges in the LP reduced cost and sent that to Keld. Keld's algorithm, I have to say, has been running steadily over the past 3 years on this problem. So it's constantly running on the server, taking a single core. Once I gave him those edges, though, suddenly he started improving. The Tor was improving by, I don't know, maybe 100 per day, well, 10.00 parsecs per day. Once I gave him that, it started improving by 1,000, so 100.0 parsecs. So since April 19th, he's improved 2.3% of the gap, which, you know, that's over 5% of what I care about is getting into 0.00. So, yeah, so there's a little bit room to improve. I have to say, I say this is my fault, these are the things, but if they could just solve instead of one LP, say solve 3 LPs, I'm pretty sure that this 3% can disappear almost entirely, and there's some hope that they change the cutting plane. So even though I do say it's my fault, well, really it's Dave's fault. Yeah, so just like to thank again David Johnson for so much inspiration. I mean, he certainly for the TSP world, he is the great champion, and he'll long be remembered and sorely missed. Thank you.